Alright, so this is part 2 of your biochemistry video notes. So this one we're going to be talking about the chemical reactions, energy enzymes. This video is also going to have water solutions and pH. That way you don't have to watch another video tomorrow night for homework. So chemical bonding. So what do chemical bonds do? What they do is it's a way for two elements to combine. It's a very simplistic definition, but for this class, that's all you really need to know. So there are two total types of chemical bonds that we will discuss in here. So first we have covalent bonds, which are when electrons are shared. Our other type then is ionic bonds, when electrons are either taken or given. So then, on to reaction. So a physical reaction is going to be something where there's a change in state. So like maybe an ice cube melting. A change in state, but you still have the same thing at the end. So same thing at the end. And then a chemical reaction then is going to be where there's a change in the product. So the reactant or reactants are different from the product. So this is going to be something like burning paper. Because you can't take those crumbled up pieces of paper or the little crisps from the fire and make it back into your sheet of paper that you had. So it completely changed. So then chemical equations, the arrow is going to indicate the process of change or the way it's going. So all of the change is going to go from reactants to products. So think about it as product produced. What's produced at the end is going to be your product. So kind of the same word. So an example is, let's say we talked about, I think, brownies earlier. We could even go back to our grilled cheese example. So bread plus cheese plus butter makes grilled cheese. So now balancing equations. So we kind of did this in class today. So hopefully you're doing all right with this. But what you need to do is pretend there's a division here. So we have oxygen and hydrogen. And of course we have the same things on this side. So how many oxygen are there? That 2. So we have 2. How many hydrogen? 2. So let's look over here. How many oxygen? Now we only have 1. But we still have 2 hydrogen. So these 2 are fine, but your oxygens are different. So what can we multiply H2O by to get 2 oxygen? So pretend there's a little 1 there. So a 2. So now though, we have 2 oxygen, but we also now changed it and now we have 4 hydrogen. So now the oxygens are equal, but the hydrogen no more. So to get 4 hydrogens on the left side, you just multiply by 2. So 2 times 2 is 4. So now you have 4 hydrogen, 2 oxygen, 2 oxygen. So now on to energy diagrams. So these show the available energy of a chemical reaction. So here's those words again. Reactants, products. So activation energy, let me change our color. Activation energy is this spot here. So the amount of energy it takes to get kind of over that hill. So reactants started here. It's the amount of energy it takes to go up and then downhill. So it's this spot to there. So energy diagrams, all chemical reactions are either going to take energy or give off energy. So we have two terms, exothermic versus endothermic. So let's think about the words. Exo means out. Endo means in. So exo, think about like insects have exoskeletons, which is why they're crunchy when you step on them. Or something like a crab or a lobster, they have exoskeletons. So exo means out. So let's look at which one's which. So exothermic, we just said, means out. So that means heat is released or energy is given off. So on the diagram, the products are going to be lower than the reactants, okay? Because this side is measuring the amount of energy. So if energy is given off, the product at the end doesn't have as much energy as it started with. So now for endo, which means in, so this takes in energy. So this is going to be the opposite. Your products are going to be higher because, like I said, energy is moving up. So if it takes in energy, the products will have more energy at the end than the reactants did. Okay? So now enzymes are also important to reactions. They're proteins, and we're going to talk about the macromolecules next week, but proteins are one of them. And they act as something called a catalyst. All right, so a catalyst is something that causes or accelerates a chemical reaction. So it's going to make it work faster. So it's not increasing the amount of product. It's not making more product out of the same starting amount. It's helping the efficiency. So think about it. A high efficient car is going to go further on a tank of gas than an old car or truck that isn't efficient. So what are they? I'm sure you see enzymes all the time, or you even eat them, but you don't realize what they are. They're biological catalysts. And we just said catalysts speed things up. So we have photosynthesis uses them, cell respiration uses them, growth in general, waste removal, or even when your stomach breaks down food. They're even used in DNA replication and movement. So how do they work? There are 3 parts to an enzyme. You have your substrate, active site, and then the enzyme itself. So your substrate, if we look down here at this picture, is this purple spot is our substrate. That's what's going to bond in. The active site is this spot where it's going to fit. And then the enzyme is your big thing here. So the active site is on the enzyme. The substrate is what's coming in to bind. And this is an enzyme reaction. Okay? And then more enzymes. So a common word used is the lock and key method. So if you think about it, if you have a key to your house, it's not going to open somebody else's house. It's only going to open yours. So the lock and key means that only certain substrates will fit into the enzyme. And we'll talk about this in class. I'll show you an example. But only certain substances will fit into the enzyme. All right, sorry about the bell. So back to this. So what happens when an enzyme is heated? It's something called denatured, is the term used. And so basically, what happens is an enzyme has a specific active site. So then if you heat this, there's our little flame here. So if we heat it, what happens is the enzyme, the active site no longer fits. So now this substrate that was designed for the active site over here, once it's heated, it won't fit there. So then that causes a problem because your enzymes can't work properly. Alright, so this is the second part of this video. It's technically the third part of the unit. So we're going to talk about properties of water, different solutions, and then pH. Alright, so there's a whole list of different water properties. We're just kind of going to go through them. We will do a lab with a few of these. So polar is the first property of water. So water is polar, meaning there's an uneven distribution. Okay, so we know that water is H2O. Alright, so you see here there's a plus charge, but then there's a minus charge here. So that means that this has an uneven distribution of charges. And it means 2 opposite poles. So polarity, think about the word pole, like North Pole, South Pole. There's two opposite poles. So you have a pole here and a pole here. All right, and then also there is something called hydrogen bonding between water molecules. So if you look right here, it says H bond. It's these little dots that bond this hydrogen to this oxygen. It's a very weak interaction, which means it can be easily broken, which is also why water has some of these other properties. So it's cohesive. So adhesive in general, I'm sure you've heard the term adhesive. Co means with. So cohesion is the attraction between the same molecules. So cohesion just means water plus water. So water molecules are attracted to each other. And then your fun little fact here is that because of cohesion, insects and spiders like this guy here can walk on water because water molecules are attracted to each other. It's also why you see this, which is a term called a meniscus. If you've ever done any baking or cooking and you measure anything, or if you remember from lab, it makes kind of like a U shape on the side of the glass because the water molecules are sticking to each other on the side. So water is also adhesive. So adhesive, just think sticky. So adhesive is the attraction between different molecules, causing it to bend. So we just talked about the meniscus, but now this is why when you put a straw in, there's a curve here. It doesn't just go straight across. So the water is sticking to the straw. And once again, don't mix them up. So cohesion is water and water. Adhesion is water and then something else. I'll just leave a blank there. Okay? So keep those two straight. All right, water is also a universal solvent. So we have our Kool-Aid man down here. That's why you can make Kool-Aid. Or today in lab you did it where you added a drink mix into water. So because of the polarity, which is, we just talked about the different poles, it can allow many other things to be dissolved in it, such as your Kool-Aid mixture. Water also has a high heat capacity. So that means that it takes a lot of energy to make this change. So the amount of energy, the heat capacity in general, is the amount of energy it takes to raise water 1 degree Celsius. So this is why water doesn't boil until it reaches 100 degrees Celsius, but a lot of other things boil before this. Water also exists naturally in all 3 states. In the 3 states, we have solid, like an ice cube, liquid, the water you drink all the time, or gas. This is like steam on the mirror after a shower, or dew on a car, which is actually, dew's a little bit more of a liquid and gas combined. But so there's 3 states of water, and it can change between these states, which if you remember is a physical change when they change these states. But so you have a physical change every time they change, but it exists naturally in all of these stages, whereas other chemicals or elements it's not the case. It also exhibits evaporative cooling, which means that water removes heat when it evaporates from the surface, like from your body. So when you get hot, you sweat, such as this poor guy down here. So when you sweat, that is water coming out of your body, but it's removing heat as well. And water also expands during freezing. So it releases heat when it expands, but it also causes things to be separated. So if you look here, the space that it was separated is much bigger because ice expands when it freezes, or water expands when it freezes. All right, so solutions. Solvent, solute. These terms are going to come up a lot. Together, they make a solution. So solvent plus solute makes a solution. Okay? So the best thing to do is look at this lovely picture down here of hot chocolate. So water is the solvent, the hot chocolate, the powder is your solute, and together, like I just said, they make a solution. So the easiest way to remember this is you think about the alphabet, so Q, R, S, T, U, V. U comes before V. So that means solute goes into solvent. So solute is what you are dissolving into the substance. So the solvent is doing the dissolving. So like we just said, water is a universal solvent. And solute is what is being dissolved. So solutes like your hot chocolate powder, your Kool-Aid mix, those are your solute. All right, so now the two different types of solutions. So we have homogeneous solutions, and then the next one's heterogeneous solutions. So homo, the root of itself, means same. Okay, so a mixture with a uniform composition throughout, like our favorite Kool-Aid. What this means is every time, no matter where you take a little sample of Kool-Aid from, it's going to be the same. It's going to be composed of the same things, no matter where, at what point in the pitcher you drink it. Now our other one is hetero. Hetero means different. Okay, so this is going to be a mixture with distinct components, like this here, or everyone's favorite, M&Ms. So it has different parts to it. Once you mix it, you can still separate all of these M&Ms out by color. If we go back to the Kool-Aid, once you mix that powder into the water, you can't get it back. It's stuck. It's a total solution. So heterogeneous solutions, think about it as you can still separate them back out. All right, and last thing, so we have pH. So pH is simply means the concentration of H plus in solution, and hopefully you know by now that H plus means hydrogen, or H means hydrogen. The plus just means it's an ion. So hydrogen ions in a solution. Acids are going to be anything below 7. Bases are anything above 7. So if we look down here at our chart, this is neutral. So water, 7, neutral. These are your bases. That green's not very bright, sorry. These are your acids. Now the closer you get to 14, that's your most basic. Okay? And then same thing, the closer you get to 0 or 1 is your most acidic. Then one last little blip here about pH. So if a substance releases H+, which we just said are hydrogen ions, when dissolved in water, it's an acid. If it releases OH when it's dissolved in water, it's a base. So these are hydroxide ions. And you know that these two together make H2O. So it just depends on what's released when it's added to water. So water, interestingly, can behave as both an acid and a base. And if you remember, like we just said, water has a pH of 7, which is why it makes a very good control. There's back to that standard or that natural. A good control in a lab setting. Keep that in mind.